look at some examples that will reveal some important properties of integrals. Consider the following. Let's look at the integral from -3 to +3 of the function x cubed. Okay, so we can do the antiderivative and plug in the values, but we can also look at this visually. And if we look at this visually, you know, we've got a cubic function, it's perfectly symmetric, and the area under the curve is negative under the x-axis, and above is positive. But the positive and the negative parts will actually cancel each other out because it's an odd function. Okay, so this integral is actually 0. And so what we have, the property is that if you take the integral from -a to a of some function f, say f of x dx, and this is actually 0 if f is odd. And what does it mean to be an odd function? Well, they have odd powers. It basically means that if you plug in a negative, f of negative x is the negative of f of x. Okay, maybe we'll make a little note there. So odd means f of negative x equals the negative of f of x. Okay, so you can always plug those in to check to see if in fact the function is odd. Now, let's do a similar example. So if we want to do number 2, we'll also go, say, from -3 to 3. Now let's do x squared dx. Now in this particular case, if we look at the graph, okay, so we're going from, say, -3 to 3. Now it's symmetric, but in this case we've got two parts that are both positive and equivalent. So what you can do is you can do the following. You can say, you know what? Instead of going from 3 to -3, I'm going to take 1/2 from 0 to 3 and double it. And so here's another property basically that's similar. So if we go from -a to a, fx dx, this is equal to the double of going from 0 to a, fx dx, if f is even. And what it means to be even is that if you plug in f of negative x, you get the same thing. So just to illustrate these two things visually, in fact we're looking at the left side, right? So if you plug in the negative values, you get the same thing as the right side. Whereas in this case, if you plug in the negative values, you get the opposite values on the other side. Okay, so these are nice properties of integrals. I definitely use them. Like in this particular case, this one is a no-brainer, right? I mean, if you see that one, you're like, oh, 0, ha ha ha, done. If you see this one, it's like, you know what? I don't want to put in the minus, a negative. It's just much easier to do it like this. So you do double 0 to 3, x squared dx. Then we get that this is equal to x cubed over 3. And I evaluate that at the 3 and 0. But the point is, it's easy to evaluate it at 3. I'm sorry, 0. Not hard at 3, but the 0 just goes away, and it's just 27 over 3, which is 9. Okay, I think that's cleaner than doing, what would we do? I'm sorry, whoa, double it. You gotta double it. I left off the 2 times. Right, it's 2 times that, so it's 2 times 9, not 9. 2 times 9, which is 18. Right, because you plug in the 3, in all cases you're going to get 9, but then you get minus a negative 9, which will give you the 18. Okay, so that's kind of nice. Let's look at another one. Let's consider the following. So let's just look at maybe like an example, and let's consider the integral from, say, let's go from 0 to, how about pi over 3 cosine x dx. Okay, let's just do this one. Integral of cosine is sine, because derivative of sine is cosine, so it's sine of x. Then we evaluate it pi over 3 and 0. Well, the 0 is 0, so sine of pi over 3. Pi over 3 is our upper pi. Pi over 6 is down here. So sine is the y value, it's greater, it's the greater one. And if you know your trig, you'll know that that's root 3 over 2. Okay, so what about the following? What if we do instead from pi over 3 to 0 of cosine of x dx? Does this make sense? Well, you can do the computation. You do the integral, you get the same thing, the sine of x, but now you plug in the 0 first and you subtract the pi over 3. So if you subtract the pi over 3, clearly that's negative root 3 over 2. And so this leads us to yet another property. And the property basically says if you have an integral from, say, a to b of f dx, I don't always write the dx, I should. But basically, what the heck, we'll write it. Fx dx. This is equal to, if you flip the b and the a, okay, so the b is here and the a is here, that's what we did here, we flipped it, it becomes basically the negative of the original. Okay, that's what it tells you. So it's just the negative of the one that you had. Okay, so a nice little property. Now, for the next one, we're going to illustrate it through an interesting example. So let's consider the following function. We've got the velocity of some particle, say, is equal to some function, and that function might be t squared minus t minus 12. And then we've got two questions that we're going to answer. We're going to find displacement and distance. So first let's talk about what the difference is. Displacement and distance. Okay, the displacement of something is where it ends up in relation to where it starts. So if you run around a track, your displacement is 0. You haven't gone anywhere, you're back where you started. And an integral will reveal that, right? Like this integral here, it's going to be 0 even though it's clearly going places. If you think of it as a curve, as something in motion. But the distance, right, if you go around the track, that's 400 meters, right? You've clearly gone a certain distance. So how do we resolve that? The distance, like here, would be almost like finding the area of both pieces. And what you would need to do is find your 0 and kind of make it, you would need to make this one positive to find the total distance. So first let's do displacement. To get the displacement, it's just a regular integral. So for displacement, you just can integrate straight up. We need to say where t is going. And so we'll say that like t is between, say 0 and 5. And so we've got this t squared minus t minus 12, 0 to 5 dt. So for displacement, you don't even have to like think much about it. You just do the integral and it's the answer. So let's go ahead and do that. We get, it's t squared. T to the third over 3. And then you get, support looking 3. So you get t to the third over 3, and then minus t squared over 2, and then we've got minus 12 t. We don't need the plus c's when you actually have points that you plug in, evaluated at 5 and 0. So the zeros are all 0, so it's the 5, I get 125 thirds minus 25 halves minus 60. Now, what actually is that? Well, it's kind of a pain, but I do want to get the answer. Okay, so let's see what we get here. 3 just, you know what? Let's just do common. Kind of a pain to do a common denominator here, but what the heck? Let's do it. So if you get a common denominator of 6, then that's going to be 250 minus 75 minus what? Well, this would be 6 times 60 is 36, 360. And the reason why I wanted to do this, so whatever that is, it's negative. Okay, so the displacement is actually negative, right? Clearly it's negative because these two terms are greater than 250 when you put them together. So we're getting a negative displacement as our answer, which is totally fine. What that means, the particle starts somewhere and it goes this way, it ends up, it's kind of before, you could say, like where it started, right? You know, with displacement, you have an x and y axis and you would have like a positive and a negative direction. But what if we want the distance? Okay, so if we want to get the distance, we've got to figure out what's going on here. And so basically we have some kind of a graph, okay? And I'll go ahead and put it down here. Yeah, let's put it down here. It's a parabola, right? So the vertex is negative b over 2a, negative b is 1 over 2a is 2. So the vertex is 1/2. And it's going to be going, like if you plug in the 1/2, clearly it's a negative number. And so what's happening, so it's going to be down here somewhere. And so what's happening is you're getting something like this. You have a lot of it is basically this negative piece, and only a little bit of it is positive. And so what you need to do is find this point, right? You've got to factor and find this point, take the integral of each piece separately, turn this one positive, and add them together, okay? So how do we get this point? We need to factor, right, instead of equal to 0. So we basically say, well, t squared minus t minus 12 equals 0. And what does that factor into? It factors into t minus 4t plus 3. Now for the negative 3, we don't really care about it because that's not in our interval. But for the positive 4, that's what we needed. And so in effect, we're going to compute the integral of v from, so if we're going from 0 to 5, this is the same as the integral from 0 to 4 of v plus the integral from 4 to 5 of v, right? And so in effect, like this is basically the property that we are emphasizing. So what is the actual property? The property, I mean, it's this, right? This is it. I'll just put it here. You have some function. You can basically split it by picking any value in the middle. Okay? So, you know, just to look at it in terms of potentially another graph. So if we put one over here, and you know, I've got some function, say from a to b. Okay, a to b. You can divide it anywhere in the middle, right? You can say, well, I'm going to put my c here. It's clear that if you add 1 and 2, you in fact do get the total. Okay, so that's what the property is basically saying. The integral from a to b of f equals integral of a to c of f plus integral of c, sorry, running out of from c to b of f. Right, that's exactly what we did here. You can basically split it. Okay, so let's see how this works in this particular problem. Okay, so integral from 0 to 4. So we already did the integral, it's really just about the bounds, right? When we integrate v, we did that. So you get t cubed minus 3 minus t squared over 2 minus 12t evaluated between 4 and 0. And then you add up the same thing, t cubed over 3 minus t squared over 2 minus 12t evaluated between 5 and 4. And then what should happen when you do these? Okay, we're a little bit out of room. I'm not going to go ahead with this any further. But this is what should happen. This one should be negative. Okay? If you put in the 4, right, kind of like before where these last terms are going to dominate, right? 12 times 4 is negative 48, negative 16. What you need to do is you need to take the absolute value of that first term. The last term, I mean, you get this, but when you subtract off the 4, right, it's going to be negative, and so you're going to be adding something that should be enough to make this term positive. Okay, so when you're doing displacement, just do the integral, no problem. Okay, you don't have to worry about it. But for distance, you must find the 0. You must do 2 separate integrals from the a to your 0, and then from your 0 to your next point. Okay? And then you need to take the absolute value. Really, to be on the safe side, you could just take all the absolute values. Because for distance, everything is positive. It doesn't matter which is positive and which is negative. You just need to take everything as a positive. That's what distance is. And velocity and speed will also have that relationship, where your speed is always going to be positive, whereas your velocity could be negative. So speed and velocity are actually similar to distance and displacement. So this property where you can like split an integral into 2 by picking a middle point isn't limited to like physics problems or distance problems. It can be useful in other cases where it might just be easier to split the integral in half. The other properties were that if it's negative, if you flip the signs, it's got to be negative. And that if you have an even function and it's from a to negative a, you can double it and go from 0 to a. And if it's an odd function, oh, those are the best. It's just 0.